Dear viewers, welcome to the UGC lecture series in biophysics. Today we are going to learn about X-ray anomalous scattering for phase calculation. If you remember, in our previous lesson, Fourier synthesis part 2, I have told you what do you mean by anomalous scattering and what are the contributions in that from the laboratory of G. N. Ramachandran from University of Madras. Now we will deal in detail the role of X-ray anomalous scattering for phase calculation. We are going to talk about resonance, anomalous scattering, Friedel's law, violation of Friedel's law, Bifer difference, how Bifer difference can be made use of to determine absolute configuration as mentioned by Professor Ramachandran group, and also we are talking about difference Patterson and what is the use of these in the location of heavy atoms in macromolecular crystallography and the algebraic proof of Friedel's law. Now, in physics, all of us know there's a chapter called sound, and there is an experiment called sonometer experiment where we use a wire which is running over two pulleys. One is a fixed pulley, another is at the end we just hang it with some weight. Okay, so this is whole is in a wooden platform, and there is a movable bridge in between, and by moving the bridge, any part of the string can be made to vibrate. Now, as you know, a fork is a prong which can be stuck with a rubber cord, and the prongs will be vibrating. So each fork has a definite frequency of vibration, 400 cycles per second, 600 cycles per second, and so on. Now, when the length of the wire kept in tension is adjusted so that the vibrating string frequency matches with the external frequency of the tuning fork, we hear a loud noise. If you keep a thin paper rider on the wire, it is blown off. This is known as resonance. When the external frequency matches with the natural frequency of vibration, a strange phenomenon happens. That's known as anomalous. Same thing happens in X-ray scattering. That's why known as anomalous scattering. Under normal circumstances, when the frequency of the incident X-rays is far away from the natural frequency of vibration of atoms contained in the molecules, the atomic scattering factors denoting the scattering power or diffracting power of each atom in the molecule is real and positive also, and this is known as F0. But when the incident frequency is closer to the absorption frequency of an atom, particularly this is made useful in the case of heavy atoms like bromine or chlorine in the case of small molecular crystallography, and heavier atoms like selenium, gold, gadolinium in the case of macromolecules. In addition to this F0, we have a correction term known as F prime, which is usually negative in the real part, and a correction factor in the imaginary part that's known as IF double prime. This F double prime is positive, F prime is negative. That this nature of atomic scattering factor becoming complex when the external frequency matches with absorption frequency of the atom is known as anomalous scattering. So strange behavior. Okay. Already you learned that under normal conditions of scattering, intensity of HKL reflection and intensity of minus H minus K minus L or H bar K bar L bar reflection will be same. And this is known as Friedel's law. But in the presence of anomalous scattering, we have intensity of HKL being not equal to intensity of H bar K bar L bar. We will give you the mathematical proof and also graphical proof, and this is known as violation of Friedel's law. Even though it is a violation, this difference in intensity between these two, which have been found in the for its use in phase calculation simultaneously by Ramachandran's group in Chennai and Piedmont Bifer in Amsterdam, this can be used to calculate the phases of the heavy atoms, and this measurement of these anomalous differences in intensities had a greater use in the case of synchrotron radiation. We will just see before you come to this chapter. The difference in intensities between I of HKL and I of H bar K bar L bar is called Bifer difference, even though Professor G. N. Ramachandran and Raman in 1950s also proved the same thing, but it is widely known in international circle as Bifer difference only. The intensity caused due to the presence of a heavy atom and anomalous scattering can be made use of as a phasing technique in locating the heavy atom. This was specifically proven by Ramchandran Raman in 1956 in the publication in Current Science. Of course, same idea was conceived by Piedmont and Byford in 1956 in University of Amsterdam. Now, what do you mean by absolute configuration, and what is the relation between absolute configuration and these intensity differences between intensities of HKL and H bar, K bar, L bar? Okay, see, this is another use of Byford difference. A structure and its inverse. When you say structure, I mean Rj, having position Xj, Yj, Zj. Inverse means minus Rj, which means minus Xj, minus Yj, minus Zj. Intensities of Bragg reflection coming from a structure and its inverse will be same. Okay, because we use only experimental intensity to arrive at a molecular structure. To avoid the mixing of the native and inverse structure, which are known as inertium of, we have to select few strong reflections and find the intensities experimentally and find the intensity difference. That is known as delta I experiment. So once you measure the intensity, these are known. But after determining the three-dimensional structure in a conventional way, from the positions of these atoms in the molecular structure, I can calculate intensity of HK and H bar, K bar, L bar, and I also can find the difference between these two, which is known as delta I calculated. Now with me, I have two types of differences. One is known as delta I experiment and delta I calculated. Even though the magnitude between these two may be different, the signs should match. Right? If the signs do not match, which means you have mixture of inertium mass. So what you do is you change the positions of all atoms into the inverse. That is known as determination of absolute configuration or inertium of fixation in crystallography. Enormous work has been carried out in the literature by the Madras group of Ramchandran and also later led by Professor Srinivasan, and one can refer to the textbook by Srinivasan and Pathasarathi towards this direction, statistical applications in X-ray crystallography, particularly on the probability distribution of Byford difference and problems related to anomalous scattering. Most of the students of Professor S. Pathasarathi, by my mentor also, they will contain chapters mainly with anomalous scattering, one or two chapters. Now let us go in detail about Patterson's and what is the relation between this anomalous scattering of Byford difference and the Patterson's. Patterson function involves squares of structure factor amplitudes as a coefficient. If you remember still, Fourier methods involve just modulus of structure factors. Of course, we need phases of structure factors also. Here, Patterson means that modulus square or intensity, which does not require phases, whereas Fourier methods give you atomic position straight away. Patterson will give you only interatomic position, from which you can calculate atomic position. Fine. Here, if you use the differences between structure factors, then you square it. Patterson itself means squared. So if you use in the structure factor differences between two structure factors, that is known as difference Patterson. If you use differences between two structure factors, f of mod f HKL and mod f H bar, K bar, L bar, which will be visibly different when anomalous scattering is there, that is known as Byford difference Patterson. Okay. Then there is some other Patterson known as dispersive difference Patterson. This denotes the difference between structure factors FHKL at one wavelength at another wavelength due to the contribution of the real part correction F prime. So which we will deal about in detail later. Don't bother. So one is known as Byford difference or anomalous difference Patterson when you use the anomalous differences due to anomalous scattering. And second is again anomalous scattering only. The real part contribution makes the dispersive difference Patterson. Let us see what you mean by anomalous scattering. As I told you, F0 is the normal part under normal condition when the incident X-ray frequency is far removed from the absorption edge of an atom. Atomic scattering F is equal to F0, which is real. But when the incident frequency globe is matching with the absorption frequency of an atom, then the real part has a correction. The real part itself has F prime, which is usually negative, and a factor F double prime in the imaginary part. F double prime is always positive. Okay. Now, When the incident wavelength is tuned, we can tune the wavelength even to the fourth decimal. Even fourth decimal variation in the wavelength causes measurable differences between f prime and f double prime. Okay, f prime and f double prime terms vary significantly even though the tuning corresponds to fourth decimal changes. Okay, let us see through the figure. So left hand side shows the figure. Atomic scattering pattern is an organ diagram where your x-axis is the real axis, y-axis is called imaginary axis. Because organ diagram is used to plot the complex quantity. F naught is real, though with the x-axis. F prime is also real. So it is again a second part, matching with on par with your F naught, same line. But F double prime, we talk about I F double prime. What is I? I is nothing but, remember little bit trigonometry, e power I theta is cos theta plus I sin theta. So I is nothing but e power I pi by 2 because your cos pi by 2 is 0, sin pi by 2, sin 90 is 1. Therefore, e power I pi by 2 is your I. So I is replaced by e power I pi by 2, f double prime is there. How to transform the e power I pi by 2 the organ diagram? From the real part vector f naught and f prime, you add 90 degree, right? You shift it by 90 degree and mark f double prime. That is why the f double prime vector is perpendicular to the real part. That is the contribution due to I, that's all. Then the total atomic scattering factor is the origin to f double prime end. So it's like a vectorial diagram, clear. Now consider figure 1b. So this shows the tuning of wavelength which is possible in synchronous radiation. Synchronous radiation, by the way, is in the physics we talk about cyclotron, high energy. When the velocity of this revolving charges matches with that of light, no, then they move so fast that the polarities between the magnets, they do not change accordingly. So that is a generally, remember accelerators, no, linear accelerators, cyclotron, everything. So we have the synchronism is lost between the polarity and the reaching of the particle. Okay. So what happens is, suppose you want to accelerate a positive charge, then the other end has to be negative charge, it will be attracted. Then by the time it takes a circular path, polarity has to change because it goes to go to the other end. But since it is moving faster and faster, before the polarity between the poles changes, it reaches the thing, it will be repelled. So synchronism is lost. So they developed a device known as synchrocyclotron. So usually the high energy, it causes, now we have about 8 giga electron volt, 13 giga electron volt using for material science and so on. Advantage of synchronous radiation is that it is a tunable wavelength and highly intense beam, you can get it, highly intense beam. Even by changing the wavelength to fourth decimal, you can get differences between f prime and f double prime. I am just showing one picture where the wavelength or frequency change and how the f prime and f double prime changes. Look at the top picture, that shows the variation of f double prime when the wavelength changes. When wavelength changes from 0, it is coming, goes up, suddenly steep rise is there. At lambda 1, it becomes a maximum and comes down. Okay, this is known as the peak. This wavelength is used to collect the intensity differences between HKL intensity and H bar K bar L bar intensity. So I told you the intensity breakdown between HKL and H bar K bar L bar intensity difference breakdown between these two happens because of anomalous scattering, and that is mainly due to the contribution of f double prime. F double prime suddenly becomes a maximum. At this wavelength lambda 1, we can find thousands of Bragg intensities which will differ in their intensity values between HKL and H bar, K bar, L bar reflector. If just you look at a point next to that lambda 2, it is coming down, and the second figure you can see that it has a dip, large dip. Okay, that is known as your edge. Okay, edge. Left hand side you see 0, above that is positive, below that is negative, which means that this f prime curve mostly it has negative values only. F prime curve has negative values, f double prime has positive values. Okay, now you know lambda 1 corresponds to the peak, lambda 2 corresponds to the edge. Now we have left hand side of the curve and right hand side of the curve. These are known as edges, left edge, right edge. So in synchrotron, before the sensitive detectors came to measure the differences, people used to measure 3 data sets. One is your anomalous scattering data is set at f double prime, where this intensity of HKL and intensity of H bar, K bar, L bar will differ. Other is dispersive difference. Suppose you collect data at lambda 2 wavelength, you look at the curve, the negative value at the more will be there, negative value. If you take any wavelength near to the starting point of the curve, no, that also you can take. Between these two wavelengths, you find enormous difference in f prime. F prime is negative. Okay, so that structure factor values will not be same. So that difference will be there. That is known as dispersive differences. Dispersive differences mean same, not the structure factor differences between one wavelength lambda 2 and lambda 4 or lambda 2 and lambda 3. Same structure factor is not there. F of HK, yeah, same structure factor, F of HK will be there. Same reflection will have different value, structure factor amplitude, when the wavelength moves from either lambda 4 to lambda 2 or lambda 2 to lambda 3. This is due to change in real part f prime. So that is why it is known as dispersive differences. Whereas if we go to lambda 1, here two reflections we are talking. Previously only one reflection, two wavelengths. Here we talk about one wavelength, two reflections, HKL and H bar, K bar, L bar. Don't confuse that. This difference we do a Patterson with lambda 1, that is known as Byford difference or anomalous difference Patterson, and to use the differences between structure factors at two wavelengths, that is known as dispersive difference Patterson. That's all. So this is very useful in the case of protein crystallography. Of course, we also have a synchronous radiation at induce. We can collect data at 1.5 angstrom resolution for protein structures. So this is just theoretically explaining. By collecting X-ray diffraction data at two wavelengths, one far away from the absorption edge, lambda 3 or lambda 4, and the other at lambda 2 near to the absorption edge, we notice that mod FHKL at lambda 4 will not be equal to mod FHKL at lambda 2 because the variation of f prime is large. As the incident wavelength is tuned or varied, the real part correction f prime in the atomic scattering factor varies significantly, and between two wavelengths in the spectrum lying at the left and near to the absorption edge, the intensity of Bragg reflection will be different. With the squares of this difference as coefficients for hundreds of Bragg reflections, a Patterson can be calculated to find the heavy atom positions like sulfur, phosphorus, selenium, gold, and platinum. This is known as dispersive difference Patterson. Also, at the f prime curve peak at lambda 1, we see nearly lambda by the absorption. K means kh is nearly 1, and lambda is a variable wavelength. The tuned incident wavelength lambda is nearly equal to the k. Lambda k means k is the absorption, natural frequency of vibration or wavelength of absorption of the anomalous scatterer. Now Byford difference becomes dominant because f double prime reaches the maximum value at lambda 1. So at this wavelength, lambda nearly equal to lambda absorption k, which is nearly equal to lambda 1. Intensity difference between HKL and H bar, K bar, L bar will be significant, and they can be measured by hundreds of reflections, and a Patterson with these differences can be carried out to get the anomalous scattering positions. Then if you do the map with coefficient FHK at lambda 1 minus mod FH H bar, K bar, L bar at lambda 1, this is known as your dispersive difference Patterson. And if you do it the same thing, HKL, H bar, K bar, L bar at same wavelength where FW prime is maximum, you do a Patterson that is known as dispersive difference Patterson. We have at lambda 1 mod HKL different from mod F H bar, K bar, L bar because IHKL is not equal to IH bar, K bar, L bar. This is known as violation of Friedrich's law. These differences can be squared. Patterson means automatically squared. This will give you your position of the heavy atom contributing to the anomalous differences. This is known as anomalous difference Patterson or Byford difference Patterson. Already we have seen that between lambda 4 and lambda 2 or between lambda 3 and lambda 2 where your real part correction is significant. So that is known as such a factors differing at different wavelengths due to real part. That is known as dispersed difference Patterson. So these are the potential applications of X-ray anomalous scattering. Since we are using multiple wavelengths, this is known as multiple anomalous diffraction data. Okay. Now we can give you algebraic proof for the Friedland's law and also violation of Friedland's law. So equation 2 gives the expression of a structure factor, atom J running from 1 to n, Fj e power 2 pi I, Hxj plus Kyj plus Lzj. If it is inverse reflection, H bar, K bar, L bar, you just change everything minus, minus, minus. That minus can be taken out in the exponent in the right hand side. That is equation 3. What is complex conjugate of structure factor F star? In equation 2, star means I becomes minus I. So I get equation 4. Now, in F star HKL, suppose you put inverse reflection, again that minus minus cancels and you get plus. Okay. Now, F star HKL is nothing but F of H bar K bar L bar, and F star H bar K bar L bar is same as F of HKL. So this is true. Now, what do you mean by intensity of HKL? Structure factor and its complex conjugate product, no? Which is equal to mod FKL square, right? Which is also equal to, since FHKL equals F star H bar K bar L bar, I can replace. Since F star HKL equal to F of H bar K bar L bar, I can replace. And simple equation tells you equation 8, I of HKL equals I of H bar K bar L bar, which means intensity of HKL will be same as intensity of minus H minus K minus L. This is known as Friedland's law. Now we will see same expression, violation of Friedland's law also, which shows that intensity of HKL will not be equal to intensity of H bar K bar L bar. It's a graphical proof for violation of Friedland's law. If you look at the upper diagram, it is going, you have to imagine that it is going anti-clockwise, lower diagram clockwise. Okay. Upper diagram, first we talk about F naught, structure factor due to real contribution of atomic scattering factor. Here light atoms will also come. Then we talk about F prime, the correction due to, in the anomalous scattering experiment, the contribution due to F prime, little f prime, real part correction, that contribution structure pattern is marked. Since, as I told you, imaginary part I f double prime is there, as I already explained you in the previous lecture, I is nothing but e power I pi by 2. Therefore, put a perpendicular and there you mark f double prime. F double prime is the contribution of structure factor due to atomic scattering factor, little f double prime. F prime structure factor is nothing but contribution to structure factor due to the contribution of the dispersed correction, real part correction, F prime. Now join the origin with the end. That is known as F of H is the total structure factor of a reflection HKL. Fine. Now, if you want to do the same thing by inverse reflection, whatever angle you are drawn, you got to put the other. Theta means minus theta because it is a down. Okay. So if you do it, we see that F of H is not equal to F of H bar. You can see easily, you can see, no? F of H bar is lengthier than F of H. Clear? So that's why expression I given you. Ordinary structure factor involving a single atomic scattering factor is replaced by 3 terms. Normal, again F prime, again I F double prime. Each is contributing to one structure factor. F naught H, then F prime H plus F double prime H. The important thing you have to note here is F double prime H includes that I part, which is, I am reflecting it in the organ diagram by 90 degree as e power I pi by 2. So this we see that the violation of Friedland's law geometrically. So I given the explanation what do you mean by F naught H, F prime H and F double prime H. The total contribution to the structure factor by the light atoms and the real part of the anomalous scattering denoted by F of H. So now F of H is nothing but summation J equal to 1 to n, contribution of 3 atomic scattering factor e power 2 pi I H dot Rj, leading to 3 components of structure factors. Then the total real structure factor F naught and F prime add together and give total structure factor due to the real part, and F double prime is the anomalous part, which includes your I term. Okay. So your inverse reflection is your I of H bar, which will not be equal to I of H. So this is called your violation of Friedland's law. Already we have seen. When anomalous scattering is a complicated derivation, it is proofs have been given. It is not so easy as a relation of proving Friedland's law. Violation of Friedland's law, a little mathematics is there, so don't bother. That is why I have given you geometrical construction proving the violation of Friedland's law in the presence of anomalous scattering. Now, if you look into that graphical equation, everything, I don't want to remember complications. We talk about an angle cos theta, which can be obtained from the organ diagram. which is of the form delta I divided by some quantity, don't bother. So your cos theta is related to delta I. In other words, if you know the by part difference of delta I can calculate cos theta. But cosine of plus theta and minus theta are the same values. Therefore, when you calculate something from cos theta, it will be having not theta only, plus theta and minus theta. Both plus theta and minus theta, the right hand side will be the same. So we have an ambiguity, right, from the anomalous scattering experiment as told by your plus or minus theta. My aim is to get the total phase angle. Yeah, that's what I want to do in Fourier, total phase angle in the synthesis, alpha. Now we prove geometrical proof, we have a relation that alpha is nothing but 90 degree plus whatever phases you get out of this heavy atom and light atom thing plus or minus theta. Now whether you have to take plus theta or minus theta, that is the question, ambiguity, phase ambiguity in case of anomalous scattering. When you take plus, you find a value, theta. You take minus theta, you find a value. Whichever value is closer to alpha r, that is the right value for the phase. So this has also been given by the paper by Ramachandran and Raman in the case of experimental result, del lysine hydrochloride. So this is known as quasi-anomalous scattering, and we have publication by Ramachandran Parthasarathy in the journal Science. So this is the most outstanding contribution of J. N. Ramachandran from University of Madras in 1956, and this work was cited when Ramachandran received the, Ramachandran could not go due to his ill health, and I also attended the international conference convened by International Congress IUCR in Scotland, and Professor Vijayan on behalf of Ramachandran received his prize. It's a prestigious Ewald Prize, no, in the year 1999. And after the death of Ramachandran, Professor Venkatesan mentioned the use of anomalous scattering and Ramachandran's contribution. He, in fact, made use of this in solving the structure of vitamin B12 when he was with the Nobel laureate Dorothy Hodgkin. So, this is a vital implication. So, this is a general thing. So, if you know the phase angle, already you know Fourier map can be calculated, electron density can be calculated, and this is again citation by Venkatesan. How he solved the vitamin B12, how he assisted in solving a vitamin B12 when he was a postdoctoral scholar with Dorothy Hodgkin, how he used the method given by G. N. Ramachandran. This already we have seen the Fourier synthesis. Many syntheses have been proposed by Ramachandran, and mainly what you want to conclude is that Professor Ramachandran, allowing his colleagues, his own student and his colleagues, come out with fantastic contributions, not only with your collagen structure and your Ramachandran diagram, but also maximum contribution in the field of anomalous scattering and also Fourier synthesis as explained in the above thing. These are the potential subjects in X-ray crystallography. So X-ray crystallography, macromolecular crystallography, connecting chapters are Fourier methods and anomalous scattering. In addition to this, they have made use of statistics also, and particular contribution I already mentioned, whatever contributed by my mentor, Professor Parthasarathy, and his students also, which can be referred from the textbook, some statistical applications in X-ray crystallography by Pergamon Press. Again, Fourier methods in crystallography. You want to refer this. Thank you.